Go on. Das kann man vielleicht auch irgendwie hier verbergen. So let me come back to what I said at the end of yesterday's lecture. So let us now take an arbitrary Riemannian manifold, open, no other condition, and then we consider the compactly supported smooth forms which embed in the L2 forms, which are defined the same way as we did it always, just completing this space in the L2 norm. And then we have our nice operator D, which maps this into the L2 space with the property that D squared is equal to 0. So this is a DGA. And of course, this persists if I put here the closure. And if the manifold is not compact, the closure is just one closed operator. This is never self-adjoint because it's not symmetric. But there may be many more closed extensions than this one. And so what we do, just to see some example, is we take the transpose D and close it up. And then we form the adjoint operator, and then I can leave out the closure because this is automatically closed. And this is an extension of the D bar. Yeah, because in principle I transpose 2 times, but you should verify this just to be sure. So that means this is a closed extension of the D bar, which also satisfies, how should I call this? Maybe I call this D tilde. D tilde is closed, and it is a differential because it comes from a differential. So now we formalize this and call the closure the minimal extension of D. And for some reason, the other thing we call the maximal extension. This would be the operator, what I called D tilde, and forget immediately. And this is dt star. And this I could call dt min, because this is really the closure. And the star operator is the maximal D. This is not the maximal closed extension in any strict sense, but is the maximal closed extension, which is still a differential. And then, of course, I have 2 Hilbert complexes in the sense I explained. And D max. And something I also told you is that these operators here generate self-adjoint extensions of the de Rham-Hodge operator. So, well, now we should not put a min or max here because this has a different meaning. So how should I actually, maybe I put it upstairs. Plus, which is defined on the domain of D min intersected with a domain of D max. So this is always a self-adjoint operator. So automatically this is actually a theorem of von Neumann, very old one. But you can easily verify this yourself. It needs a little work. But then you see if M happens to be compact, then this looks very much like the closure of the D. And it actually is. And this is another proof of the essential self-adjointness in this case. But in general, this is not so. So then because we have another operator which is self-adjoint, which I define as the analogous thing. What is happening here? Now with the D max intersected with dom D prime max, D star, D prime max. So D. Yeah, so this is the. And you can see that these are actually different in one important case. So let's assume now that M bar is a manifold with boundary. With compact boundary. So M bar is itself compact and of course oriented. I mean, we should keep this in mind. And then we have these two self-adjoint operators, and the homology, cohomology, we could also write as min-max for the moment of M bar is the kernel of D max min with, of course, the Z plus grading, which I ignore for the moment. And, of course, these two are different. So H min is the ordinary cohomology of M, so it does not feel the boundary, and H max is the relative dm, which clearly tells you that these two operators are different. So that shows if I do not have compactness, I have to expect that I will have many self-adjoint extensions. And of course, this shows you a class of distinguished self-adjoint extensions if you succeed in finding many of these closed extensions of D which are squares, which are differentials, whose square is equal to 0. This animal likes chalk, it seems. And we have a general definition that the maximal cohomology is called the L2 cohomology of N, which already has been used. But this for quite a while, this was not clear what it really means, the L2 cohomology. So you admit any L2 chain, L2 form, which has the differential in L2, and take this complex, which is the largest you can think of. Okay. So of course, one wants to compute this for a large class of Riemannian manifolds. So I don't consider closures and so on, just say I have a Riemannian manifold, what structure ever I would like to compute the L2 cohomology in order to have a topological description. Of course, in general, this is an unsolvable problem because there's no technique which could help you to compute this in such a generality. But a good class would be M, which can be compactified. So we find some space dm, of course, not necessarily what you normally think it is, which is compact in a suitable topology, and M is open and dense in M bar. This is a good class. And there are many complicated constructions, like for locally symmetric spaces, this so-called Satake compactification, the huge class of compactifications where M is compactified by adding smaller dimensional locally symmetric spaces in a suitable way. And of course we know what this means from simplicial complexes. This has already been discussed. And let me show you my favorite simplicial complex. So this is something in R3 which we can easily visualize. It is a perfect Platonic body. And to understand it, we could unfold it in the plane. So then it would, it's not very nice, roughly look like this. So what happens here? So here are these bottom points. But the top point appears 3 times. And then you see that this is actually, if you now identify 2 neighboring triangles, then this is a flat manifold. If you take out these points. These points, of course, are the singularities. And we see on this picture very nicely that these are cone points, and the link is half the circle. And this is 180 degrees. If it would be the full circle, it would be smooth, but it's not smooth. It has 4 conic points. Okay, and actually, such things did exist for some time. That's the famous Tetra Pak, was, for milk and something similar, cacao, and they smoothed out these boundaries in a very nice way. So if you cut off these 4 points, you really see it. Unfortunately, they do not exist anymore. So then you see this problem. For example, if you ask yourself, so what is the Euler characteristic? Let me call this thing M, and the compactification again M bar, which is M disjoint union, these points 1, 2, 3, and this one. So the conic points. What is the Euler characteristic, or let's say the L2 Euler characteristic? But this should be the same as the L2, as the normal Euler characteristic of this object, which is the sphere. So it should be 2. And now we know that if this thing would be compact, then it's just an idea. It should be the integral over M of the Euler class, E of Nabla. But we have our doubts because E is a polynomial in the curvature. The curvature is 0. So this integral exists, it is perfectly 0. So where did the index go? Only possibility is that it's sitting in these points. Yeah? So maybe for this I take color because it is quite important. So we have these singular points here, and there, with the identification, there should be a contribution. Do it better here, then we have no identification. We see there should be 4 contributions, which by symmetry should all be the same. So it should be 1/2. But how can I get this 1/2? Yeah, this is a big question. Maybe the simplest instance of analysis on a singular space. So how to compute one-half from the conic points. Actually, this is not a simple thing, even though it looks simple. You have to do a rather involved analysis. So you have to describe, first of all, the operator. In a neighborhood, and then we could also say tubular neighborhood of the singularities, which we already know. This is the cone. How did you write this again? The pointed metric cone of 1/2 of S1. That's what it is, right? Okay, but there was work before by Atiyah-Patodi-Singer which studied boundary value problems, BVP, boundary value problems for D, but also for more general operators on manifolds with boundary. Where, now this is an important assumption, it's not strictly necessary, but to understand what is happening, where the color is flat. So the color is something like 0 epsilon times the boundary with induced metric dt squared plus g of dm. Then you can separate variables and so on. I mean, then this object looks like having here little cylinders. So, of course, it goes out smoothly. And then they proved an index theorem, which was actually, at that time, the time was 1975, so 10 years after the second proof of the index theorem appeared, 10 years later. So they actually apologized for that in this paper. But there was a difficulty, namely that you cannot do this by imposing local boundary conditions on the boundary. And this was, everybody was used. Elliptic boundary value problems were very well studied, also for higher order operators. But all the boundary conditions were local. They were given by local operators. And you all know the Dirichlet problem. Then you say the thing should be 0. You know, so the restriction to the boundary is 0. That's a local operator. Or you could take the Neumann problem, where you say, in second order, the normal derivative along the boundary is 0. That's a first order differential operator along the boundary. And the trick is that now you have to do something completely different. And what they did is the following. So study D on the color. So we take our D here. That implies D becomes an operator of this form. There's some element gamma dt plus A. So gamma squared is equal to -1. Gamma anti-commutes with A. These are tricky things you have to find, and A is self-adjoint in the space L2 of Dm. So I don't want to write it explicitly, but it's the first order, the self-adjoint extension of a first order some elliptic operator. So since M is compact, we can say with discrete spectrum. And this operator plays an important role because now the boundary, the domain of D is equal to the, let's say, alpha in L2 of M, or it's enough to take, with your notation, the L2. That means the square integrable smooth forms, such that so I don't have really a name for this. A certain projection PA of alpha at 0 is equal to 0, where PA projects onto the positive eigenspaces of A. And this is not a local operator. Yeah? So you take this section, you expand the section in the eigensections of A, which is a discrete series, and you project away the positive eigenvalues. And the solution is then that the index, this is still the self-adjoint operator, but this, you know, we do this here. Now this depends, this is plus, so what is it? It is the integral of the Euler class for the plus operator as we would expect it. But there is an additional term from the boundary which is minus 1/2 the dimension of the kernel of A plus the so-called eta invariant of A, which is another non-local quantity. Namely, we define the eta function of A, which is the sum over all lambda in the spectrum minus 0. This we should not use. And then we take the modulus of lambda to the minus z and multiply by the sign of lambda. Okay, positive eigenvalues come with plus, negative eigenvalues come with minus. So if this would be a matrix, a symmetric matrix, you put z equal to 0 as you may in that case, and you see it's just a signature of the matrix. So this is therefore they call this the spectral asymmetry. Namely, if we had an involution, a self-adjoint involution, which anti-commutes with A, then this would be automatically 0. But now we are looking at something which is reasonable only in even dimensions, like this one, which would always be 0 in odd dimensions. So this is an invariant of an elliptic operator in odd dimensions. Okay, so this is the important point, and it may well happen that this is something rather interesting, especially interesting from the point of view of number theory. So this was okay. And of course, Chigga thought about this, like many others. And Chigga discovered that the eta A is naturally attached to the manifold where the boundary is coned off. Boundary is coned off. We have seen this, that you just put a cone there. Namely, and this is the case we are interested in that case, we obtain that the index of D plus is this integral, again, minus 1/2 the eta function, this nasty kernel disappears. So this is completely natural, and this is now the eta A computed on the conic neighborhood. Yeah? So that, in other words, it is the eta function is defined on the link, which is the same here. But it appears, so to speak, in the index formula directly without this very nasty quantity, because it's almost impossible to compute in general. But this is very well to compute. And now we solve this mystery. For the tetrahedron, this will be 0, but this can be computed. And it turns out to be exactly equal to minus 1/2, and so we get our result. So this is was something to be learned at that point and had a long development. And now, so to speak, in the second part, I want to study special singular spaces which are compactifications of manifolds. And of course, these will be pseudo-manifolds, but I'm not going to consider this in this abstraction, but I consider such spaces in some high-dimensional Euclidean space, always equipped with a standard metric. So in order that you can easily have induced topologies and so on. So what do we want? So we go back to the simplex. This is not a simplex anymore. So I do it here again. And so there's a remarkable phenomenon which is on the basis, or at the basis of simplicial theory, namely that the n simplex is composed of open simplices in various dimensions. Yeah, so I take the interior, the open interior, I take the faces without the boundary, I take these edges without the edge points, and I take the points. So I get, it decomposes in 0 dimension, 1 dimension, 2 dimension, 3 dimension, and in general, so we get something compact from open manifolds. So that's one of the ideas. So we take a space W, say, should be, so first of all, I do not want too many of those. So let me say compact is not necessary, but it is easier, and should decompose into manifolds. So that means this would be the first axiom. Is a disjoint union of certain elements which lie in a subset of the power set of W. So some subsets, first of all, which is, or such that S of W is locally finite. This is a nice assumption. That means every point has a neighborhood which is met only by finitely many x. So this is the case in the simplicial situation and in many others. But Markus has already mentioned a second condition which is very useful, namely to say that for two elements, x and y, in this partition, namely that x intersects the closure of y bar, so this should be non-empty, then it follows that x is actually contained in y bar. Okay? This is what we want. Just look at the, just take this edge here and take another edge then the closure of this edge contains these two boundary points, but it does not intersect x. Yeah? But it the closure of the face that intersects each of these three things and actually contains them. So this is so this implies x bar equals x and a union of other faces. Which faces? Those which where x intersects y bar. Yeah, this is the so-called condition of the frontier. Which for a naive person like me causes some confusion, because what actually is the frontier? Who is familiar with this word? It's not surprising because it's not in use anymore. But if you look at Bourbaki, volume 1 of Topology, then you find the frontier. This is just what we otherwise call the boundary. So let me call it the frontier of A equals the closure intersected with the complement of A closed. And why is this a condition of the frontier? Well, one should define the boundary as the closure minus the interior. Then this is always contained in the frontier. And this condition means that, remark, 2 implies that W is closed, which otherwise would not be true. And you can find, describes explicitly the difference between, so the difference is the frontier of A minus the boundary. I don't know, what is the topologist's naming of this? I think this is not in use anymore, right?
Yeah, it's usually not discussed anymore, but the terminology is that of a topologist also, frontier and boundary.
Okay.
This would be used in that sense.
Yeah.
Also, but it's true the frontier is usually not introduced anymore.
No. But it's awkward then that this name is preserved, the conditioner. Anyway, it's a relatively simple fact, but it's very useful to have it. And of course, this behavior is quite often the case. For example, the one Marcus described of the algebraic varieties. Algebraic varieties are closed, and you see that the closure of the top variety comes as a union of smaller varieties, and exactly in this sense. So, and also this is always satisfied.
Sorry?
Yeah?
Would you like to recall what is S of W and I of W?
This is the power set. So the the set of all subsets, right?
Okay, and
S is just the name for this decomposition. I have a number of subsets which might maybe.
So S arises from.
Yes.
Is introduced.
Yeah.
Okay.
Axiomatically, yeah.
Okay.
And what if there is only one piece, one stratum in S? In other words, if W is
Yes.
an open submanifold, so I
It's
don't
not
quite see why it has to be closed.
Yeah, this is so.
So
It's sitting in Rn, yeah? So it has the induced.
Right.
This is not abstractly meant. Everything is sitting in Rn. And this is a consequence of this thing. But of course, what you might think of, if you take something like a simplicial complex.
Let's just say I take an open interval in R2.
Yes.
Or,
Yes.
then both conditions
Then
are satisfied, right?
No, it's not closed. You see, if I have the open interval, I take the closure, I get the closed interval. Yeah, and this condition says that the closure is a union of strata. What you can do, of course, is you don't take R2, but you take, let's say, the parallel strip which contains the interval. This is a manifold. This thing is in there, and then it's true. Then this is, if I have one stratum, this says that the stratum is closed. In the relative topology. So if it's in all of Rn, then it's not enough. Then you should restrict to some open set which contains it and not the boundary.
But if there's only one x,
Yes.
the condition just says if x
Then
intersects its own closure non-trivially, then it must be contained in its own closure. But any set is always a subset of its closure.
Yeah, but it's
So
not
isn't it
equal to its.
vacuously true?
It is not equal to its own closure. No, if you only have one in x, then the whole condition reduces to x contained in x square, implies x is contained in x square, which is true.
Right.
Yeah.
But it need not be closed. It's true even if for an open interval, isn't it?
Let me see. Yeah, maybe this, yeah, you are right. This is a little too weak. So you could, let me see. Let me look at an equivalent relation. You take x bar minus x, and this should be a union of strata. Y intersecting x bar non-trivially. This is, of course, a little stronger.
Then that's stronger.
Yeah, this is. Maybe this is, I should formulate it this way to have this, yeah?
Sorry, so also in the first line, here you wanted to say that you take the disjoint union over all y such that x intersection y is non-empty.
Yeah, it's
Okay,
non-empty. And x equal to, y not equal to x, yeah, because otherwise I could leave this out. Mm-hmm. So you see that this is the formula for dx. And yeah, probably I wanted to do it this way. It's dangerous not to look at what one has written. Yeah. Yes, yes. So I want it in this form. If you take the boundary of a stratum, then it's a union of two strata. If there are no other strata, then there is no boundary, right? So then it means X needs to be closed. Yeah, so this is a very general condition which implies something which you otherwise would actually I wanted to do, yeah, I didn't look at what I had written. I wanted to have two versions because these are purely topological conditions. But I'm sitting in Rn and 2b, 2a, sorry, first a, then b. 2a says that each x, which is a stratum in the set, is an embedded submanifold of mu. This is, of course, a much stronger condition. Which implies, for example, so this implies, let's say 2a implies that X is open and dense in X bar, which is also called locally closed. And this is equivalent to saying that X is the intersection of a closed set and an open set, which is the complement of dx, because this here implies dx is closed. Now, and everything is done in R mu, so this is true. Yeah, so this is a nice beginning, but of course, it doesn't say anything if you think of this example about how the boundary of a stratum is connected somehow to the stratum itself, to the interior. And this was a big question, of course, for a long time, which was addressed by Whitney in his very fundamental papers, which have already been quoted. And he came up with a condition which is really not easy to understand. So this is the condition 2b. Well, first of all, I would like to formulate a weaker condition, which is satisfied in all the examples you showed, for example, and is satisfied for the simplicial. If X intersects the closure of Y, and X, of course, is not equal to Y, then the dimension of X is smaller than the dimension of Y. This is an axiom now, right? It does not follow from what we have said before. And the true condition, which is actually called Whitney's condition B, is a bit more complicated. So actually, before I formulate it, I introduce a notation which is very convenient. Notation. X intersects Y closure non-trivially, then we write X is less or equal to Y. And this is, maybe it's also a little exercise using 1a through 2b0. show that. So this is an order relation on this set S of W is a partial ordering. Yeah, so this is really useful. Normally little use, but you can, the graph, let's say if you have finitely many such things which arises, has interesting information. So what is Whitney's condition B? So let x, so this then of course means x intersects the closure but is not equal to y. And then take a point P in X, or maybe we call it X, little x, because remember, we are always in our mu. Assume sequences X contains xn, which converges to X. But this is also an accumulation point of y, so I can also find a sequence yn contained in y, which converges to this point, such that. Okay, two conditions. The first condition is that the tangent spaces Tyn of y converge to a space tau as n goes to infinity. So how should we think about this? Normally, this is not well defined, of course, but Tyn is sitting in our mu, right? Because we are in our mu, and it's equivalent to the orthogonal projection onto Tyn, topologically. And so this is a compact space, it's a Grassmannian, and every sequence actually has a convergent subsequence. And in this sense, these spaces converge to some other space, okay, of the same dimension. The second condition is even more strange, but it's very easy to formulate in Rn. So these 2 points cannot be equal because this is one stratum and this is a different stratum. So you divide by the length of this vector, the unit vector, and these unit vectors are supposed to converge to some unit vector which Whitney always called L, because he thinks of the line, the connecting line between these two. And we are not ready yet. So assume all this, then L is an element of tau. The one-dimensional vector is contained in this space. So this is not a trivial condition. It looks rather involved. And if all of this is satisfied, so if 1a through 2b are satisfied, then this W is called a Whitney stratified subset of R mu. Yeah, so rather simple. I mean, you don't need a fantastic amount of axioms, but you have to pay a price for that. That the most important axiom is not at all intuitively clear. But first of all, let us discuss some consequences and then some examples. So now I should be careful. What did I? Yeah, so an important thing is the so-called depth, the depth of a stratum. Okay, the word stratum I have not used, so this is equal to pure stratum. So then now we are in complete accordance. So it means one of those elements of the partition. I mean, this approach is more geometric, so it does not emphasize the skeletons and how they grow, but it looks at the constituting particles, the parts, and wants that these parts are manifold. So that's really a different point of view. So we have seen already in the definition of a topologically stratified space that you use, even in the definition, you use induction, which is okay, but of course not extremely intuitive. Then you have to do 0, 1, and so on in order to understand in the dimension. But there are other quantities, integer valued functions on this space, which are very useful in doing induction, and also in cases where you can't use the dimension. So the depth is called, for some reason, kappa of x, but kappa, the Greek kappa is the letter which is very little used, so here it has a good appearance. So consider a chain in this ordered set, S of W. And a chain, of course, is a totally ordered set, so we have a stratum x0, and call this chain of length k. Then the depth of the stratum x0, so kappa of x0 is equal to the maximum of all k in C plus a chain of length k starting with x0. So if you look at the tetrahedron and you take the interior, the open interior, which is a stratum, so depth is 0, yeah, because nothing is larger than that. If you take a face, then the depth is 1. You take an edge, then the depth is 2, because it borders at many. And if you take a point, then the depth is 3. Okay? So in this example, it's the same as the dimension, but normally this is not the case. Okay, this I wanted to introduce. What else? Yeah, then we have some other terminology. X, stratum X is minimal if y is less or equal to x implies y is equal to x. So there's no smaller stratum, and it's maximal the same if y greater or equal to x implies the same thing here. But of course there could be many minimal and many maximal elements. So x is a maximum if y is less or equal to x for all y, and a minimum, sometimes also called a lower bound or upper bound, y is greater or equal to x for all y. Just terminology, but it shows how nice this ordered set is. Yeah, then we always speak of a dimension. So the dimension of W is the maximum of the dimension of these submanifolds, which in an abstract setting need not exist, but here we know always that this is less or equal than the embedding, the surrounding dimension mu. What else? Okay, then another important, so W regular, and I call this dimension MW. This is the disjoint union of those x which are of dimension, sometimes also called the top. The top stratum is maybe not the right name for this, because these may be several. And also a stratum need not be connected. That is another point to keep in mind. And very often people say, okay, you look at all the connected components, but it's not clear a priori whether this is still an admissible decomposition, but in fact it is. And of course then the singular set, which is often just, for example by Marcus, always written like this, is just W minus we assume, this is an assumption, not a difficult one for simplicity, that the singular set is actually the boundary of the regular set. Yeah. This need not be the case. Is, for example, the Whitney umbrella shows, yeah? Which something we will come to a little later. So that's just some formal things. We can also define the skeleton. So WK is just the union of all strata which have dimension less or equal to k, which satisfies all the axioms. So then we get the same filtration as in the topological case, and again the differences are unions of manifolds of the same dimension. So that's all very well. Is there anything else? Yeah, this is too complicated to be. A little exercise here. Characterize the situation that x bar intersected to y with y bar is not empty. Yeah. For example, I could ask, does it imply that the dimension of x is not equal to the dimension of y? You find this assertion in some recently published papers, and so it's good to check it occasionally. Okay, now, I mean, it's nice to have this little apparatus, but of course the essence of such things are the examples. So let's start with something non-trivial. So let's assume that this is a manifold with boundary. And the question is whether this satisfies all the axioms. Well, it's very easy largely. So these are two are manifolds, submanifolds of R mu. If the manifold sits in R mu. And it's a partition. And it satisfies this assumption because dm is by definition m bar minus m. Yeah? So m bar is m union dm. dm, this satisfies axiom 2. These are submanifolds, so this is 2a. This is also satisfied because the dimension is 1 less than the dimension of the manifold itself. But what about the condition B? That is not so clear. So now we have to check this condition. Now we have to recall how the manifold and its boundary are pasted together. So we have a U is an open neighborhood in M bar of dm such that U is homeomorphic to 0, 1 times dm. But not only homeomorphic, we actually want it diffeomorphic. This is easily said, but it's actually a non-trivial problem. You have to think about this for a moment. What does it mean? Because we have a closed interval here. And the easiest way to think about is to think that this is the restriction of a smooth map between Euclidean spaces to this space. So this sits in R mu. So the whole thing sits in R mu plus 1. And you want that this diffeomorphism arises as the restriction of a smooth map from R mu plus 1 to R mu, which is a homeomorphism on this set. So that's perfect definition, but it is a little difficulty which we know how to handle, but one should see it. So what does it give? This gives, so this map has a name. Which direction do I want it? maybe we go this way. Or maybe rather this way. Doesn't matter because otherwise, so this defines a function t, which is just the projection on this interval p01 times, this should have a name, which is called a boundary defining function. So that's a smooth function, smooth and positive, such that dt of p is not equal to 0 anywhere in the domain of this function. Yeah, and this is the way I paste these two things together, yeah? Using, if you like, this function, which is very nice. Now we could take the gradient of t with respect to the standard metric of the surrounding space R mu. And this is a nowhere vanishing vector field in this neighborhood U. And points inward. Everywhere. Okay, so that's this is what this color is on the other side. So we also may use the flow phi t of S, the flow of this vector field. So now we can look at this condition B, which is actually not difficult. So what do we need? We need a point P or point X in the M. And we have a sequence Xn which converges to this. It's also contained in dm. And another sequence Yn which is contained in M. And what we have to understand is what does tangent space do as n goes to infinity? Well, the easiest thing is you look at this vector field, which is sitting in here, if Yn is close enough to the boundary, which we may assume. And then we have the vector fields which are parallel to the boundary, which are also transported to U. So this is an m-dimensional space. And when I move with this space to the boundary, it's exactly the same space, defined by the same vector fields. So the limit of this space is clear, and we can call it Tx of M. So if you think M extends over the boundary, then this would be literally true. But you see that there's nothing that can happen. It goes smoothly to this point. And then we look at the line which Yn minus Xn. And this is something we study in Rn. But what do these points actually do? What does it converge to? I mean, the straight line may not lie in the manifold. Yeah? But you can take the geodesic between these 2 points inside the manifold, and that will converge to this expression, obviously, because the closer these points come, and you use exponential coordinates in the tangent space, then you see this. So this converges to some tangent vector, which is also in here. It's really not difficult. I mean, the whole structure gives you this right away using some elementary differential geometry. So MdM is a Whitney stratified set, which I may abbreviate like this. Okay, that was the simple case, because in general we do not have such a beautiful description like this collar. Where is my collar? Here. Yeah, this is normally not present. So let's look at another example. Example 2, the spirals, because I want to look at 2 spirals. So 2a, this is the Archimedean, but here called the slow spiral. It is too slow to be good. Namely, this is the following set. I define C, let's say Cs of t, e to the minus t times cosine t sine t in R2. And let's say t in R plus. So then it has a boundary point. So this starts somewhere here, and then it spirals around 0, and as t goes to infinity, it comes to 0. So in my terminology here, I cannot make this closed at that point. So I define the set which we want to analyze as the image of Cs, of course the point 0, so this is S of W actually, and the point when t is equal to 0, which is a boundary point, and that is just the point 1, 0. This is not important, so this would then be this point here, yeah? So this is a perfect stratification in the sense above. I mean, these are submanifolds of R2, embedded submanifolds. Maybe if you don't believe this, you should study it yourself, but it is an embedded submanifold. The homeomorphism between the open half line and the image. This is a limit point, of course, of this set, so it must be there because we want to have something closed. This is the initial point, and the closure of this is this set joined with these 2 points, and of course these are closed, so there's no problem. So this is all okay, and again what is left is the condition B. So condition B wants to know what happens to our tangent spaces, and so we have to compute the derivative. So let me call this thing here E1 of t, because this is a standard unit vector which goes around. and then we have C S prime of t equals e to the minus t. So, and then what happens? If I differentiate this, I just get cosine t sine t plus, this remains, but now I differentiate here. And I call this e2 of t. And this is really e to the minus t, e minus e1 plus e2. And of course, these two vectors are orthogonal. This is a moving frame, right? Okay, the tangent space to this submanifold at the point P is the space generated by this vector, and the length of the vector is 2 times square root of 2 times e to the minus t, so it's non-zero. Everything okay. But now I want a sequence of points, xn equals cs of tn. So then we have C prime, or let's say the tangent space at C of Tn, Cs of Tn, to this thing which has no name actually, let's say the regular part, is the span of e to the minus Tn, e1 minus e1 of Tn plus e2 of Tn. Okay. And so the corresponding unit vector, so C prime S of Tn divided by its norm is minus e1 of t plus e2 of Tn divided by the square root of 2. So this is very harmless. And we have to assume that this converges to some vector tau as n goes to infinity. So what does it mean? What does convergence mean here? Yeah, I mean, we can write this vector here, of course, because it could be in principle any unit vector. So we have E plus E2 of T0. Okay? It will be of this form at some point. And of course, we may have convergent subsequences because S1 is compact, but they could have many limits. But at least modulo 2 pi, I should have that Tn mod 2 pi converges to T0. Otherwise, I cannot fulfill this assumption that this converges. Okay? Now, what is the other thing? I want to understand the connection between this point and then the stratum, which is smaller. And of course, the only interesting case is 0. This is not an interesting case because it's a manifold with boundary. We did this before. So, so I subtract 0, which is not so interesting. And what we get is, for the Cn, this is E1 of Tn plus E2 of Tn. No. This is only it, if I divide by the norm. Yeah? So if this converges, then E1 of Tn, n will converge to E1 of T0. And so then the two will never match. Okay? So this is a very nice example. So this is where condition B fails. This is a little confusing, really, because it's not so clear why this is so. And actually, we could do something in using a fast spiral, e to t alpha, now for alpha greater than 1, E1 of t, and look for the same problem. This is, in fact, isomorphic in any reasonable sense to this thing. Yeah? Whatever sense you can think of. It is restricted to each stratum. It's smooth. It's a smooth embedding inside this set V. And now we could look at the, so this I call the fast spiral. Now I have to again do a difficult computation for the tangent vector. And again, I think that safely this can be kept outside. And then I get minus alpha t to the alpha minus 1 times E1 of t. And then I differentiate the other part. And I get this. Okay. Now I look at the crucial thing. Where do these unit vectors go? And now I have to be a little bit careful. Of course, this drops out. And upstairs I leave the following, minus alpha t to the alpha minus 1, which is positive, times E1 of t plus E2 of t, divided by alpha squared t to the 2 alpha minus 2 plus 1 squared. Okay? Now I put little n's here. And look what happens. So these two vectors are orthogonal, so I can treat them separately. Suppose Tn goes to T0, maybe mod 2 pi, doesn't matter. And then you see that this is as large as this one. So this converges to minus EI of T0. And this guy disappears because this goes to infinity. But then we are done. Just looking at the thing as before. So the fast spiral satisfies B. Yeah, you just need a tiny little tip and it's done. But it's something to keep in mind, that it is not a trivial fact. It needs some thought. Just remember this. It's very elementary, but it shows how tricky this notion is. The next time I will study what we have done to some extent, the Whitney umbrella. And their only condition B. Everything else we have done already. Yeah. Okay. Now we make for the boat. So, I mean, I have the problem that I have my car and I have to bring this to